Hello, this is a makeup video on repeated measures analysis of variance. And to go briefly through the purpose of repeated measures analysis of variances, the unique thing that this type of analysis does is it allows us to compare differences related to an independent variable when the populations are not independent of one another. When rather than three groups being measured one time, you have one group being measured three times. So this corresponds to the repeated measures to the paired samples t-test, except that in the paired samples t-test, you only had two times that the same people were measured. But this can extend it to many other measurements. Each subject in a repeated measures analysis of variance has to be tested at all times, or this doesn't actually have to be times. It could be at all dosage levels, at all types of brief intervention. But it's important that everyone has complete data. Anyone who doesn't have complete data will be dropped from the analyses. There are methods to do something like a repeated measures ANOVA that allows missing data. And there are also methods to generate data when data are missing, which I'm a little skeptical of, but we will discuss at a later point. So the reasoning basically is that repeated measures is intended to answer the question, is variation within individuals when they're measured on the same dependent variable? So they're measured, for instance, on pain. We're using a 10-point pain scale. And they are measured multiple times on the dependent variable pain. And is it attributable? There are differences in measure, which they will undoubtedly vary in their pain level, likely attributed to whatever is happening between the occasions of measurement or the types of intervention, as you could say, or is it likely just due to chance? So this is also called the within subjects design. So the intervention happens within people rather than between people. The dependent variable is the outcome that's measured, and the independent variable are the conditions that are controlled or that are naturally occurring. So the F ratio, which is what the overall test in a repeated measures is, the F statistic is what the analysis is tested against, is the variance due to the independent variable divided by an error term. Now, the variance due to the independent variable, the numerator includes various kinds of random error. And it always does in all F ratios. You always have to take into consideration that with sampling and other difficult to capture conditions like individual fluctuations, there's going to be error variance. So the variance due to the factor includes some kind of an error term. The denominator is the error term. The difference in repeated measures from normal analysis of variance is that the error term can be reduced. And what it can be reduced by is variance related to the subjects. We call it subject's variance. It's variance related to the cases, not between cases, but within cases. So when we have, let's say, 3 points of measurement, the independent variable has 3 levels, and the each individual is measured on the outcome 3 times. Then we can actually estimate how much variance in the dependent variable measures, the outcome measures, are predictable by that person alone, taking out of consideration, setting aside consideration of factor A, how much can be estimated just related to that individual. And once we get the estimate of that, that is no longer random. Whatever we can predict is not random. And so it can be reduced from your error term, thus making your error term smaller. And that's wonderful because you want a smaller error term. And although it's also reduced in the numerator, that is not going to have an overwhelming impact on the it will have an impact. If your variance due to the factor is 0, your F is going to be 1. But as your variance due to the factor increases, the relative impact of the error plus the variance due to subjects in the numerator will be less than it is in the denominator. So the things that we need to work with in order to do a repeated measures are we need to know the number of people who are being measured repeatedly. And again, you have to have complete data. You need to have an independent variable that varies within people according to the number of conditions. That's J. Okay, so factor A is one thing at level J. It has another nature system. It's very useful, I think, to give examples here. So let's say that your factor is dosage and you have 3 levels. So then you're going to have 1 variation on factor A at the first level, 1 variation on factor A at the second level, and 1 at the third level. And of course, you need sums of squares as in order to get mean squares, the variances. Sums of squares are an essential step towards the variances, and they're also used directly in a lot of manipulations to variance terms and to correlational analyses and things like that. So you might say, well, why don't we skip directly to the mean square variances, the mean squares? But because you want to compose multiple mean squares, you have to have all the sums of squares components. So your total sums of squares is everything. It's the variance due to factor. It's the predictable variances, variance due to the individual people, the variance that has been modeled because you have people repeatedly measured, and it has what's called SA, which is the remaining variance that isn't modeled by either the factor or the predictable variance within subjects. So that's SSA is the factor, SSS is the individual predictable differences, and SSA is your overall error term, where the error term is composed of your normal residual error, which is reduced because you've deducted the SSS, the predictable variation, because subjects are due to individual differences, because subjects are measured multiple times. Your degrees of freedom and your mean square variances or your mean squares are composed as usual. We can break this down. I am not going to go through all of these individual equations, except to note that your factor of interest is sums of squares due to the factor or the independent variable. And that is the mean of each individual over their levels minus the grand mean times the number of people who are measured. I guess I am going into these formulas just a little bit. That's the one of the greatest interest. The SSS is not used in the F-tests, and it is called error between in SPSS. It's the value removed when you calculate SSA, and it's the predictable error due related to an individual regardless of which level of the factor they're being measured at. So SSA has this deduction from the overall error term, the deduction of SSS, which you can manipulate algebraically, but we don't need to do that particularly. So the F statistics, as I said, are calculated in the traditional way. The F for the independent variable, which is what you're going to be interested in, is the variance due to A divided by the variance due to SA, which is your new error term. It's the error term, remember, with the variance due to the individual subjects, SSS, removed. The mean square error for each of these is the sum of squares associated with that mean square divided by its degrees of freedom, and the formulas for the degrees of freedom are found over to the right on this slide. And the effect size for repeated measures ANOVA are a partial eta squared term, again, like we've seen in factorial ANOVA, where you have in the numerator the sums of squares associated with the independent variable, but the denominator includes the removal of the sums of squares attributable to subjects. So that is actually a place where you need this term. If you're doing this in SPSS, some versions of SPSS don't provide an eta squared, partial eta squared for SSS, and I'm trying to think whether you would ever need to calculate this, but this is what it would be, is you would be removing that term. So, and the alternative way, which you're more likely to have if you've calculated this, is kind of by a simple substitution. SS total minus SS subjects is equal to SSA plus SSSA. The residual variance after you've SSSA being the residual error variance after you've removed the subject's effect. Okay, so we're going to move over to Excel to look at data in an experiment in which 4 people with chronic pain were measured at 3 different dosage levels of a drug during a 3-week treatment program with rest periods. So they had chronic pain, so it was expected to endure. They were not getting a cure, they were just getting palliative. They received the first dosage level, then they had a rest, second dosage, and so on. The dependent variable was a measure of their pain. So we're going to move over to Excel, and I'm going to stop for a minute, pause the recording, and get my Excel set up. Okay, so here we see the same data that was in the slide. We have the 4 subjects. They were measured 4 times. They 3 times each, I'm sorry. They were measured on pain, so that's the subject A had a pain score of 2 at the 300 milligram dose, a pain score of 5 at the 200 milligram dose, and a pain score of 8 at the 100 milligram dose. And we are only going to test the hypothesis for now that we'll test the differences between, as it were, dosage levels if we pass the omnibus null hypothesis, if we find that there is the difference somewhere between some combination of dosages. So I've already put in the grand mean here for, that would be the mean of all 3 columns for all 4 people, and the what I've called here the trial means, that are the mean for the 300 milligram dose, the 200 milligram dose, and the 100 milligram dose. What we also need in the repeated measures ANOVA, which we never had before, is the subject means. And that would be this term for SSA. No, I'm sorry. This would be this term for SSS, right? This is what we can model due to predictable differences between these individuals, and because this is an individual's mean across the J groups. And so we're going to put this in. The subject mean for the first person is this individual score, and so on. And here are their means. So if we want to calculate SSA, what we need are the means of each group. Okay, so this term here is across the individuals within a group. So this was within an individual across groups, and this is across individuals within groups, minus the grand mean. So we're now going to calculate that. We're going to add up each deviation, and we are going to each squared deviation, and we're going to multiply that times the total number of people who are repeatedly measured. I'm going to put those, I think, here. So those are the SSA components. And so for the first group, that's going to be this value minus this value, total grand mean, squared this one is going to be, no, I'm sorry. I often get confused with these things. So this is simply this minus the grand mean squared. Okay, it's over individuals, but within a group. And then we're going to have this, but it's going to be wrong because it's not going to correctly reference the first cell. Again, so that's that, and that's those. And we can check them. It's always a good thing to check. This has a deviation of 0.33, and when you square that, first of all, you're going to have a negative 0.33, you're going to have a positive value, and it should be around there once you've squared it. So our sums of squares for the A factor is, first of all, don't forget to multiply by the number of people. So it's that times the sum of that value, and that value. So that's our A. Our degrees of freedom for A over here is J minus 1. So the degrees of freedom, we have 3 levels, so J is 2. And why that's already in there, and our mean square for J would be our sum of squares for J divided by our degrees of freedom. Now we calculate our sums of squares SA, which is, looks like that, well, it's the one that is currently so we're going to calculate SSA in kind of an ugly way because it's actually going to be quicker in Excel. We could calculate SSA using the other terms, but in this case, I'm just going to work through this formula here. I don't know if it'll stay correctly written, shown on the screen, but the SSA kind of raw formula. And so to get that, we need for each cell, we need the cell value minus the mean for their column minus the mean for them as an individual plus the grand mean, and we're going to square that term. Dragging these down is, you have to get everything to have the right dollar signs in SPSS, which I find really boring. So to have the correct reference in the, I think this will stay correct, and I think my guess is Debbie knows this, but I'm going to guess it. 0.44, 0.11, does that look right? So that would be 4 minus 4, which is 0, minus 5 is -1, plus 6.3 is 5.3, equals 5.3 squared. Ugh, of course I'm wrong. Do that again. I'm sorry, but you know, I check things. Why shouldn't you check things? So the individual score is a 2. The mean for their group is a 4, so that's -2. The mean for them as a person, right? 2 minus -2 is bringing us to 4. The mean for them as a person is 5, so 4 minus 5 is -1, plus 6.3 is 5.3. Why am I getting that again? Pretty sure I did these right, except that I don't. All right, so I'm going to do these the hand way, which I will always advise you to, when in doubt. I don't know whether I'm a terrible model or a good model of what to do when you're uncertain, but I'm some kind of a model. So this one is fine. We're going to do this one kind of the hand way, equals their individual score minus their group score, which is 4, minus their subject mean, which is, do I go around? Go ahead, plus the grand mean. Then I put in the dollar signs wrong here, and I don't quite know why, so I'm not going to worry about it. So that is going to be, let's C10. I can keep the C10. And you have to square that term. Did I square the previous term? No, of course I didn't. It was 0.44. I had put in the dollar signs right. So I5 means that you're always looking at the 5th row. And put those things in right. Isn't that wonderful to know now? But fortunately, it should work now, except that I'm going to have to fix that. So note, by the way, that, again, another way of checking, 5 minus 6 is 1 off from its individual relationship to the group mean, and the error term is like the one that's 1 divided off. I'm not making sense. So I think we can check this visually, but since I don't make good sense, we're not going to. So this value we're going to copy here, and it should copy correctly, E8, I4. Let's make this completely over again. If I have, it's not working. So this is G4 with referencing to all the G8s and referencing to I always, that should be right. Okay, so now for SSA, we sum all those values. Make sure I remember to square all of these, square all of these, square all of these, square all of these. Okay. So this is our SSSA. God for that. Okay, so our mean square, SSA, we need to know our degrees of freedom. For SA, our degrees of freedom are the number of people who are measured repeatedly times the number of repeated measurements. So that's 3 times 2 is 6. Our mean square SSA is going to be 4.67 over 0.77. I'm going to get rid of some of these decimal places because they're ugly to look at. And also a degree of precision we don't need. And our F ratio here is the mean square A divided by the mean square SA. Remember, S is the variance minus the error variance minus that can be attributable to individual differences. So we have an F-test here that's 32.57, and you can check that against your critical value. I'm just going to tell you, well, we'll check it against our critical value. We'll check it with the P label in a minute in SPSS. So of course we have our assumptions in the F-test, that the observations between subjects are independent from one another. That means that person A is not related to person B. They're not the same person, although there is the assumption that there is a relationship between the person measured at level 1 of the independent variable, level 2 of the independent variable, and level 3. The populations are normally distributed on the dependent variable, and there is the test of sphericity, which is new. It's a little bit analogous to the homogeneity of variance test. The homogeneity of variance tests look at comparing the variances between groups. Sphericity looks at comparing the variances of the different scores between each level, the variances of the different scales. So it's the within subject variances should be equal at each level of the factor. So the difference between dose 1 and dose 2, the distribution of the differences between dose 1 and dose 2 should be equal to the distribution of the differences between dose 1 and dose 3, distribution of the differences between dose 2 and dose 3, and those would be all for our particular study that we've been looking for. You will have the homogeneity of variance test when you have also between groups factors, and we'll look at that in another video. So we're going to look at this in SPSS now, where we can see for one important thing, the test of the assumptions. So I've opened these data in SPSS. This is a file called repeated simple. It should be in Blackboard. And you see this, these are exactly the same data that we were working with before in Excel. To do this in SPSS, you go to Analyze. You have to go to the general linear model because compare means doesn't let you do anything where people have been measured more than once except the paired sample t-test. And you go to a menu you haven't seen before or an option you haven't used before under the general linear model, which is multivariate. Multivariate means that you have multiple dependent variables. Oh, I'm sorry. We're not going to go to multivariate. We're going to go to repeated measures. Repeated measures is what you use when you have repeated measures. Multivariate is for multiple dependent variables, but it is a more complex kind of design that makes different assumptions. So we're going to go to repeated measures, which is a specific option. Our within subject factor name is the different doses, and we have 3 different doses. So we tell it we have 3 levels of the independent variable. And our measure name is pain. That's the outcome variable that we're interested in, is variance in the outcome of pain. It asks us to define those, to tell them which variable in the data set corresponds to which levels of the independent variable. And since we only have 3, it's pretty easy. Dose 300 is going to be the first, where the first set of outcomes are located, dose 2 and dose 100 milligrams. We have no between subjects factors. That would be like, we'd also randomly assigned people to an exercise regimen. So that of the people who were measured, we had twice as many, and the second group had an exercise regimen and the first group did not. So we're not doing that for now. We're not going to do post hocs until we find out if there are actually any differences, and probably there is a post hoc test that's available by default in SPSS with repeated measures, which is going to be the one that we're going to look at. And our options are, we might as well get the descriptive statistics, the estimates of effect size, and that's pretty much all. The homogeneity tests are only useful when there are between groups that are intended to have homogeneity. We will see the assumption of sphericity, which is provided by default. And we could look at the residual plot. I think I'll talk about residuals when we get to multiple regression. So now we're going to just say continue. Here's what is included in the analysis. Here's our descriptives. You will remember these are the dosage levels we saw before, the pain levels we saw with the associated dosage levels before. We have, this is the overall test, F-test. Here's the F statistics of dose on pain. So this is, does dose matter in terms of pain outcome? It has, regardless of which row you look at, the significance level is 0.02. So if you have an alpha of 0.05, you're going to reject the null hypothesis. Your partial eta squareds are very large. The significance level, one of the things that's making this larger than given these very strong effects, is the lack, the very small number of people. And you should be aware that the reason that you do not report an effect size unless you have a statistically significant outcome is because you can have large effect sizes when you don't have significance. And that doesn't make any sense to say, well, I have no reason to think that the results are not due to chance, but here's how large the results are. So what you're going to see is that you have these four columns, these four rows: Pillai's trace, Wilks lambda, Hotelling's trace. So these are different ways of conjuring the F. They have different values, but under the value, it's not, when the F differs, then you have to make a decision which one to use, and you should make that decision before you begin. We're going to assume Wilks lambda. It's really the one that you most commonly see. It's not important in this case to go into their differences. In social science research, I usually see Pillai's trace or Wilks lambda, but Wilks lambda the most commonly. And you'll notice in this particular case, but not always, the values are the same. If you see a change, it's a large change in values, it will usually be at Roy's largest root, which is, I believe, a much more liberal test. This is the test of sphericity, which is your important assumption. And this is tested with something called Mauchly's W. It is the test, if you look at this, the error covariance matrix of the orthonormalized transformed dependent variables is proportional to an identity matrix. Well, what does that mean? What that means is that across the dependent variables, the covariances among the pairs of outcomes the distribution of people's outcomes at each levels are, when you covary those distributions in a standardized way, they are essentially the same. They're not significantly different. And these values are related to the, if this were significant, which it is not, you would use one of these three values, probably Greenhouse-Geyser or Winfeld, to adjust the degrees of freedom for the F-test below. So this test of the effect of dose, which will kind of replicate this test, but it you'll see that it will have different significance values, and it will have different F values. This is actually what you'll more normally see reported, but people report either one. But the test of within subjects effects is essential if you also have between subjects effects. The multivariate tests, if you have, for instance, two groups, each of which is being measured 3 times. So we just have one group that's being measured 3 times. If you had two groups, then the multivariate test would test the whole shebang between groups and within groups. And that would not break down into within and between effects. So if you do have that set up, which we're going to look at in a minute, then you need to look at the tests of within subjects effects, and that would be what you would report. So I think that's why this is more traditionally reported. You'll notice, though, that the values are very consistent. If this were for any reason, I was doing repeated measures, I would report the within subjects effects. But you do see Wilks lambda reported with a fair frequency. In this case, we can use the values under sphericity assumed, and then you'll notice that you have these other rows for if you cannot support the assumption of sphericity, and they correspond. Greenhouse-Geyser, for instance, corresponds to where you see these epsilons, which, as the note says, can be used to adjust the degrees of freedom. And you'll see that Greenhouse-Geyser, for instance, adjusts the degrees of freedom. Winfeld does not in this case, because you have non-substantial departures from the assumption of sphericity. And we're going to stop here for a minute before we look at anything else in SPSS. Actually, there's one more thing I want you to note in this output, which is I said that we were not going to ask for post hocs, and that's because the post hoc that is often of the most interest is provided by SPSS by default, which is whether there's a trend. And in other words, whether a linear, or when you have more than 2 levels of repeated measures, a quadratic function will fit the relationship between pain and level of dose. And so we see here that we have a significant trend. In other words, not only is dose statistically significant, but there is a constant line that can model with reasonable precision a straight line relationship going through dose 1, dose 2, and dose 3. So that's a test of a linear relationship. The quadratic relationship, which we wouldn't really expect to be significant, is not, but it would be reasonable in this case to expect that where we have high dose, this is pain, this is dose. We started out with a high dose, medium dose, and low dose. So this is our low. And we had little pain here, varying across 4 people. We had more moderate pain here, points varying across 4 people. And we had, at the lowest dose, we had the most pain with variability across people. Actually, I haven't drawn this tremendously well because this should really just be dots along this line, because dose didn't, there was no variability around the dose level. Nonetheless, we have a linear trend. A straight line can model this quite well. And I believe that's going to be all for, almost all. So why do we like this? Repeated measures are intrinsic to some kinds of research, like longitudinal studies, if you can control the independent variable, like is everyone measured at 6 months? Is everyone measured at 1 year? If people are measured at variations in time, repeated measures will work. Repeated measures can be much more powerful and consequently require fewer subjects, because you're reducing your denominator in the F-test, then you will, everything else being equal, you'll have a more powerful test, and it's a money saver. And if you have difficulty recruiting, or you plan to expect to have difficulty recruiting, it can be a useful thing to build into the design when it will work. So that's all for this presentation. It was probably quite a bit.